Hello and welcome again to my Physical Science online video lecture supplement series. In today's video mailbag, I wanted to go through a couple of the exercises that were assigned in the homework for chapter 5 of our book, which would be the chapter on temperature and heat. So let's see what the actual question is asking. The question which was asked was, can you please provide the answers for exercises 2, 4, 6, 8, 10, 14, 16, 18, 20, 22, and 24 of our homework for chapter 5? I think that it would not be proprietary for me to provide quite so many solutions via a publicly available video on YouTube. I don't think that the textbook publishers would be very happy with me if I worked through every single one of the even-numbered examples in their book. But I am willing to work through a few of the examples. Happily, this email question kind of came back with I've asked the person who emailed this to please narrow the list down, and the response I got was basically just work whichever ones are appropriate for this course and the quiz that we're going to have over this chapter. Well, all of them are on the homework, so all of them are appropriate for this course, but I guess I'll just pick a couple and work them. So I'm just gonna work exercises 6 and 20 from chapter 5, which is of course on heat and temperature and the ideal gas law. So let's look at what these two questions are. So the first of these two says the temperature of outer space is about 3 Kelvin. What is this temperature on the Celsius scale, and what is it on the Fahrenheit scale? So we want to basically figure out what is the cosmic background temperature of space on our Celsius scale and on our Fahrenheit scale. Before we begin, it may be helpful to review the little important equations that are included at the end of the chapter. This is a little section that the textbook publishes right before the exercises. So here are a few of the important equations that are in that section. And in fact, what we're wanting is to get from Kelvin to Celsius. So this is how you get from Kelvin to Celsius. And we also wanted to get from Kelvin to Fahrenheit. Well, this is Kelvin to Celsius, and here's Celsius to Fahrenheit. So if we do this one first, then we can do this one next to get both of those temperatures. Okay, so we were given the temperature in Kelvin, which is 3 Kelvin, and we have this conversion that says that the temperature in Celsius is equal to the temperature in Kelvin minus 273. Okay, so that means that the temperature in Celsius is 3 Kelvin times 1 degree Celsius per 1 Kelvin minus 273 degrees Celsius. That's basically how we can interpret that. So this whole thing right here is 3 degrees Celsius, so that minus 273 means that the temperature in Celsius must be negative 270 degrees Celsius. Okay, so that's our background temperature in Celsius. The next thing we want to do is find what is the temperature in Fahrenheit. And we're given that the temperature in Fahrenheit is 1.8 degrees Fahrenheit per 1 degree Celsius for a change times the temperature in Celsius plus 32 degrees Fahrenheit. So that means that we have a temperature in Fahrenheit of 1.8 Fahrenheit per Celsius times negative 270 degrees Celsius plus 32 Fahrenheit. And of course, this temperature in Celsius we got from part A to this problem. So out comes the calculator. We had 270, which is negative, times 1.8, and then we need to add to that 32, and you get minus 454. So the temperature in Fahrenheit is minus 454 degrees Fahrenheit. Okay, so that answers that exercise number 6. Exercise 20 says that a fire breaks out and increases the Kelvin temperature of a cylinder of compressed gas by a factor of 1.2. What is the final pressure of the gas relative to its initial pressure? So this is, I suppose, one of the harder questions that you can get in the physical science course. So let's go ahead and review our equations sheet again. So this is the rest of the important equations from chapter 5 of the text. And basically these second pair of equations are both have to do with the ideal gas law. The one that we really want is this one right here. The P2 over P1 equals V1 over V2, T2 over T1. Now this comes from the ideal gas law. The ideal gas law, recall, says that the pressure of a gas times the volume of the gas should be the number of particles in the gas times a universal constant known as the Boltzmann's constant times the temperature of the gas. So the second equation that was shown there is basically equivalent to saying, okay, well, let's take an initial condition for each and a final condition for each, and we'll just divide the left-hand side by final conditions of pressure and volume, and the right-hand side will use the initial and final conditions of number, and of course the Boltzmann's constant is a universal constant, and the temperature. Okay, so in the actual question, the fire has broken out in such a way that the final temperature has increased to 1.2 times the initial temperature. By the way, these temperatures should be in Kelvin. So both are in Kelvin. That I'm highlighting because sometimes you might get a problem in which the initial and final temperature is specified in Celsius, or the initial is given in Celsius and it wants to know the final. You've got to convert to Kelvin first in order for all this to work. Okay, well, we've just been given that the final temperature is 1.2 times the initial temperature. So that was given in the problem. We have to make an assumption here, which is that the cylinder of gas is rigid. So rigid cylinder means that the volume does not change, so V1 is equal to V2. And we're going to make the assumption that this is leak proof. Okay, so that means that no particles escape from the cylinder. Both of those are generally valid assumptions if no information is given about the cylinder in question. Okay, so what do we end up with here? So we had P1 over P2, V1 over V2 is equal to N1 over N2, T1 over T2. And the rigid condition basically means that these two cancel. The leak-proof condition basically means that these two can cancel. So you're left with P1 over P2 is T1 over T2. And what we want to know is the ratio P2 over P1. So that's the reciprocal of this side, so we need to take a reciprocal of both sides. So P2 over P1 must be equal to T2 over T1. Okay, and T2 over T1 we can get from over here. It was given because T2 is equal to 1.2 T1. That means that T2 over T1 must be equal to 1.2. So P2 over P1 must be equal to 1.2, and that's the answer. Well, there's two examples from the text that I have worked for you. I hope that you find this video helpful. I know that some of these problems are very difficult problems for those of you in the physical science course, so hopefully having seen them worked will make this a lot easier, and hopefully the publisher doesn't get too annoyed at me for working two of their examples from the text. So thanks for watching.